Good morning, students. Welcome to computer period, and in today's class we are going to basically do a revision of certain topics which we had covered in the month of April. So in this class we are going to take up the topic list manipulation, and in that we'll be revising binary search. So we are going to see what is binary search. As you can see here, we have a list called numbers, and it contains some numbers over here. The precondition for binary search says that the list should be sorted, and preferably in the ascending order. Your list should be sorted. And you can see over here that all the elements are in the sorted order, that is, they are in the ascending order. And I have also mentioned the indices of each of these elements at the top. So let us start with binary search. Now, as opposed to binary search, we have something known as a linear search. You all know what is a linear search. In linear search also an element is asked from the user, and that element is matched with each and every element in the list, and if a match is found, then it is printed. So over here also we are going to see how with linear search we can do this. So let's start with the program for binary search. Now firstly, in binary search what happens is you ask for a search element from the user. The user will enter a search element. For example, the search element here entered by the user is 50. So now let's see how this 50 will be searched in this list by the user. So firstly, I will write the elements in the form of a logical fashion. And this is the list, and now what we are going to do is over here we are going to divide this list into two equal halves. So for doing that we need to first find the midpoint of this list. So we take the first initial part, that is beginning, and the last part, that is end, or we can take it as last. The first index is big, and the first index I'll be providing it over here as 0. This is big, and last is provided as the n, that is n minus 1, and in this case it is 7. N is 8 over here, that is, this list contains a total of 8 elements. Now we will calculate mid. That is the central point of this list. So what is mid? Let's see. Big plus last divided by 2. So mid equals big plus last divided by 2. So over here big is 0, last is 7 divided by 2. So we get the midpoint as 3. 2 3s are 6, and so we get the midpoint as 3. That is, this has been calculated as mid. So now we have mid as 24 over here. Sorry, mid is 3 because this 3 refers only to the index. But if you want to access the element, then you will have to write it this way: numbers mid. and numbers mid is what? It is 24. So now we'll check, is 24 equal to the search element? Answer is no. So because they are not equal, now we will check whether element is less than the mid element. Is 50 less than 24? Answer is no. Is 50 greater than 24? Answer is yes. So that means now it is clear that my element lies in this part of the list. Understood? So now how to do this? Over here we have to again calculate mid. So let's calculate mid again, but before that we will be resetting beg. Beg should be now set at this location, that is 4. Understood? So how to calculate beg over here? It will be set to if the search element is greater than the mid element, then beg will be equal to mid plus 1. Understood? Beg will be equal to mid plus 1, and in the opposite case, last will be equals to mid minus 1. So now let us try out. Now you can see that this part of the list, the shaded part over here, we are never going to visit this shaded part. Now it is clear that our element lies in this part of the list only. So binary search means every time you will divide your list into two equal halves, and the search element will always lie in one of those halves only. So we will never be searching or visiting this part of the list. We will only be searching in this part of the list. So it saves our time in looking for every element or performing a lookup of every element in this shaded part of the list. So let's calculate mid once again. Now mid will be beg plus last, that is 4 plus 7 divided by 2, that is 5. Okay, 2 5s are 10. So now our new mid is this. So now what is mid? What is numbers mid? It is 46. So we'll see, is search element equal to this 46? Answer is no. Is search element less than 46? Answer is still no. Is it greater than 46? Yes. That means we are never going to visit this part. Understood? We will be searching only in this part. So for this again beg will be equal to mid plus 1. So here we will be writing beg. This is beg. Okay. So now our new beginning is 6 and our last is 7. Let us again calculate mid. 6 plus 7 divided by 2. It is 6. So now mid is also this. Now beg is 6 and mid is also 6. So now what is the element here? 50. So now is numbers mid 50 equal to search element 50? Answer is yes. So a match is found. So it will be printed as, position will be printed as mid plus 1. This is the position of the search element. Element is found in the list. So here our search ends. Now there could be a case where you are looking for an element which is not there in the list. For example, let me take the element as 16 and let's see how we can work with that. So I am going to create this list once again. So this is my list, and we are going to look for the value 16 in the list. So as usual, we start from big as 0 and last as n. So over here we start, big is 0 and last is n. So last is 7. We calculate mid. So it is 3. Mid is 3. So that means this is mid. Now this is mid, and what is numbers mid? Numbers mid is 24. So numbers mid is 24. Does search element equal this 24? Answer is no. Is search element less than mid? Numbers mid? Answer is yes. That means it should lie somewhere in this part. That is in this part of the list. Okay. So what will happen? This whole area will be shaded because we are never going to visit that area again. So now we are going to search over here. That means we need to set last as mid minus 1. So this last will be removed from here, and we will be having this last, which is mid minus 1. Let us calculate mid again. 0 plus 2 divided by 2, that is equal to 1. So now our new mid is this 12. It is 12. So is search element 16 equal to 12? Answer is no. Is 16 less than 12? No. Is 16 greater than 12? Yes. That means this part will never be searched. Now we are left with only one element, that is 15. But we will move according to our plan over here, because search element is greater than mid. Hence beg will be set to mid plus 1. Because we are assuming that element lies somewhere after mid. So our beg has to be reset. So this is beg over here. And now beg and last, they both are the same, that is one element only. Again we will calculate mid. That is 2 plus 2, because they both are the same, which is again 2. So this element is big, this element is last, and this is also mid. And what is the mid element? It is 15. Understood that? So mid element is what? 15. So is search element equal to numbers mid? Answer is still no. Is it less than 15? No. Is it greater than 15? Yes. So we have to set beg equals mid plus 1. That is, now beg will be set to 1 more than mid. So beg is set to this element over here. So this is a point where beg exceeds last. And this is our stopping point. We need to stop over here. Okay. And when this condition becomes true, it means the element is not present in the list. So this we will be seeing in the form of a program. So for doing the program, let us move on to our computer. So let's see a program on binary search. So we first start with creating a list, and we will be accepting the list from the user. Hence I have written it within the eval function. Now I'll be asking for a value from the user. Now we will start our binary search program as according to the video which I have explained. We will use a while loop. Now for this we need two variables, that is beg and last. So beg is going to be 0 and last is going to be len numbers, which will give us the size of the list minus 1. So we will calculate beg plus last divided by 2. If numbers mid is equal to element, then print element found at position mid plus 1 and break. Else we will use elif element is greater than numbers mid. Then if we know that if element is larger than the mid element, the middle value, then it means that we have to shift the position of big to mid plus 1. Else if element is less than numbers mid, last is equal to mid minus 1. If beg is greater than last, if beg exceeds last, then print element not found in the list. So we will run this program and see. So first we need to enter the numbers in sorted order. So I am entering the numbers in the sorted order here. It is a precondition, that is you have to enter the numbers in sorted order. Now element to be searched, I am giving 40 over here and we have a problem. So list indices must be integers or slices, not float. So there is a problem here, that is I have to use floor division over here. And I'll copy this list from here and I'll paste it here. Element to be searched is 40 and we can find that it's giving the position as 8. Let us check. 1 2 3 4 5 6 7 8. So yes, we are getting this answer, and let us run this for an element which is not there in the list, say 13. Sorry, I just gave the wrong value. So I will again paste this and give a value 13. 13 is not found in the list. So this program works perfectly over here. You can see that over here we are calculating the midpoint. We are checking whether the middle element is equal to element or not. And here we are checking whether it lies in the initial part of the list or in the latter part of the list. And the moment beg exceeds last, it means that element is not found in the list. So this is the program for binary search. So this was binary search. We saw how to code a program for searching for an element in a linear list using binary search. In my next class, we are going to take up another topic, that is insertion and deletion in a linear list. Thank you.